All right, we've looked at pure substances previously, but now we need to look at mixtures. In particular, we need to look at homogeneous mixtures, which are also called solutions. So our job in this section is to consider how much of a substance we have within a nice homogeneous mixture or a solution. All right, we can look at our solution. Now, a cup of coffee is a nice solution. We know that a solution is a homogeneous mixture, and we can adjust the amount of a substance within a homogeneous mixture. So we could add more or less sugar. If we had less sugar, we would say it is dilute. If we added more sugar, we would say it's concentrated. But we want to know actually how much stuff we have. So instead of looking at dilute and concentrated, we're going to look at the actual numbers. A solution has got two components. It has a solvent and it has the solute. The solvent is whatever we have the greater component of, or if it is in water, water is always going to be the solvent, and when we have something inside the water, we're going to call it an aqueous solution. So we're going to have a solute, usually the stuff in lower amount, or whatever we put into the water, and we have the solvent, what is ever going to be the greater amount. Once we're done, we're going to have the solution, so we have three things. Solution is the combination of the solvent and the solute, and again, if it's in water, we're going to call it an aqueous solution, and water will always be the solvent. And again, we can look at units like, or amounts like concentrated and dilute. It just doesn't really tell us very much. That's just qualitative. We instead, because this is chemistry, we want to know how many moles of something we have. So we're going to introduce a term, molarity. Molarity is moles of solute over the total volume of solution in liters. And so we have molarity, moles of solute per total volume of the solution in liters. So how might we do this? Well, we have a soft drink, and we know how many moles of sugar it has in this soft drink, and we want the molarity. We know that, by the way, we also call it a molar concentration, or the molarity of the solution. We know that molarity is moles of the solute, which in this case is our sugar, divided by the total volume of the solution in liters. So we got to remember volume of solution in liters. So let's do our conversion. If we have 355 milliliters, we know there's 1 liter for every 1,000 milliliters, and we're going to have 0.355 liters. Our molarity is going to be 0.133 mole divided by the total volume of 0.355 liters, and we're going to have a concentration of this solution of 0.75 molar of sucrose, aqueous, meaning 0.375 moles of sucrose would be in 1 liter of the total solution. So continuing, we want to know how many grams of potassium iodide is required to make 500 mils of this concentration. So if we had 1 liter, we'd have 2.8 moles, but we only have half a liter. Let's make sure we can do our conversion. We know there's 1,000 mils per liter. So this is going to give us 0.500 liters. And we want to know how many grams this is. Well, please note that the volume of the solution in liters multiplied by the molarity is going to give us moles. And so if we take 0.500 liters and we multiply by 2.80 mole per liter of the potassium iodide, we're going to get the number of moles of potassium iodide in the solution, and this is 1.40 mole. We need the molar mass. The molar mass of potassium iodide, we can look at the periodic table and calculate this, and this is 166 grams per mole. And we know to go from moles into grams, we multiply by molar mass, so 1.40 mole multiplied by 166 grams per mole is going to give us a total mass of 232 grams of potassium iodide in that 500 mils of solution. So how would we prepare this? So to prepare a solution of known molarity, you take and you weigh out your solute. You know how many moles you need for your solute because you're going to know what the molarity needs to be. So you're going to weigh out your solute to get the correct number of moles, and you're going to add your solvent until you have a certain volume. Now this container is called a volumetric flask. They only have one line on them, and that is when the total solution has a given volume. So you weigh out the amount of solute, add water, shake it up, and you're going to get a solution of known molarity. So let's look at a cholesterol question, just because it's maybe a little more interesting than just straight chemicals. If we have 250 milligrams per deciliter of cholesterol, and by the way, that's the units your cholesterol comes in. So let's consider this, 250 milligrams of cholesterol per deciliter of your blood. Now note a deciliter is equal to 0.1 liters. And the first thing we want to do is get the molarity. So let's get moles. If we have 250 milligrams of cholesterol, we know there's 1 gram for every 1,000 milligrams. We can look up the molar mass of cholesterol, but in this case we're given it, and we know we're going to take and get 1 mole of cholesterol for every 387 grams of cholesterol, and that is going to give us a total here of 0.00065 mole of cholesterol. All right, that's the moles. Now that is, here our milligrams are in a deciliter. We need this per liter. Now remember our molarity is moles per liter. Because a deciliter is 0.1 liter, we are simply going to divide this by the volume in liters, which is 0.1, and this is going to give us a concentration of 0.0065 molar of cholesterol. All right, so we got moles of cholesterol. Now the second question is, just because why not, why don't we figure out how many total grams of cholesterol you have in your body? So let's look at this. If we have a volume of blood of 5.2 liters, we know that our cholesterol is 250 milligrams per deciliter. So let's look at this in deciliters. We know that we have a deciliter for every 0.1 liters. We know that we have 250 milligrams of cholesterol for every 1 deciliter, and this is going to give us our milligrams of blood, which are milligrams of cholesterol, which works out to be 130 milligrams. We know there's a gram for every 1,000 milligrams. This is going to give us a total of 0.130 grams of cholesterol in your entire blood. All right, continuing on this chapter, we want to consider dilutions. Now, dilutions can come in many varieties, but we're going to do this pretty consistently. We are simply going to lower the concentration of a solute in a solution by the addition of pure solvent. When we do this, we're going to get a lower concentration. Dilution is the method in which we do this. If we started out with a nice solution here, this is copper sulfate, and we added some water to it, excuse me, copper nitrate, we're going to get a more dilute solution. And you can tell this by looking at the color. It's a lighter shade of blue. So let's think about this one. We want the molarity of the potassium permanganate in this solution, and we're looking at 4.75 grams of potassium permanganate in this container. And so what is the molarity? So if we have 4.75 grams of potassium permanganate, we know that the molar mass of potassium permanganate is 1 mole for every 158 grams. And yes, we're going to get that off the periodic table. We're going to discover that in this solution we have 0.0301 mole of potassium permanganate. If we want to know what the concentration is, we're going to realize that in this container we have 1,000 milliliters. We know that's the same as 1 liter. So we're going to have 0.0301 moles of potassium permanganate in 1 liter, giving us 0.0301 molar of KMnO4 aqueous. And again, aqueous means the stuff dissolved in water. So let's go back to dilution, because yes, the previous slide was a non sequitur. If we take the volume in liters and we multiply by the molarity, you're going to get moles. Now, if we're simply adding water to something, the moles are going to be constant. And because the moles are constant, this allows us to make the math very straightforward, because we can say that the volume times the molarity initial is going to equal the volume times the molarity final, because in this case, the moles at the beginning are going to equal the moles at the end. All we're adding is solvent. So we're going to get a nice clean equation out of this. And our equation is this. It says that we can look at M1, L1, but we're going to call this volume 1 times concentration 1 is equal to volume 2 times concentration 2. You can do this in any order. Now, note, it doesn't have to be molarity. It can be any units of concentration that you want, as long as these two units are consistent and your 2 units of volume are consistent. So we can say M1 times V1 is equal to M2 times V2, and as long as they're the same in terms of our units, this completely works. Any other units of concentration will also work as long as they're consistent. So let's do one. We're going to take and label this. We know that we have 8.50 liters. So let's say that V1 is 8.850 liters. Now our concentration is going to be 5.00 molar. Now we know we link these, and the key on the linking is the word of. If we have something of, this volume of, it means that they are the mix or the set that we're starting with, the pair we're beginning with. And we are going to dilute to a total volume at the end of 1.80 liters of whatever the final concentration is, which is what we are solving for. So we're going to take 0.850 liters multiplied by 5 molar equal to 1.80 liters multiplied by C2. And when we do our math, our concentration here is going to be 2.36 molar. V1M1 or V1C1 is equal to V2C2. All right, now what volume of, volume is what we're solving for, of 10 molar, which is going to be our concentration, C1, V1 and C1, do I need to make a volume, V2, of 250 mils of, again, that's going to be C2, 0.150 molar of nitric acid. So our equation here is going to be V1 C1 is equal to V2 C2. V1, we don't know. C2 is 10 molar, is equal to V2, 250 mils, multiplied by C2, 0.150 molar. Now I know you're going to have the urge to put the concentration here in liters. You do not need to. If you leave this in mils, this one works out in mils. Again, we can use any set of units as long as they're consistent on both sides. We're going to end up in this case with a volume of 3.75 milliliters. And if we take 3.75 milliliters of nitric acid and we add enough water so that the final volume is 250 mils, we will have a 1.50 molar solution.